And I graduated from US school on top of it. I went to the US to get my PhD and continue my specialty training in orthopedics. So you can see the map down here. This is the US map, and the red color is where Ohio State located. It's kind of in the Midwest, but in the east side of the Midwest. So today, we choose this topic because it's a very generalized topic. Can you hear me? Can everybody hear me?
Yeah.
Okay,
Yes.
good. Right. So I think this topic is very generalized in orthodontics and also very fundamental or basic. So we're going to talk about those kind of very basic information and may not be too much deep into the subject. Okay. But I think first we want to know, why do we do orthodontics? Okay. And does anybody know why we want to do orthodontics? Yeah, it's hard for you to hear from you, but I think that's kind of tough question I'd like to ask. In general, orthodontics has a health paradigms, okay, healthcare paradigm shift, right? So in the early mid-20th centuries, orthodontics is focused on disease control, okay? So, but with all the changes over the years, now our new wave is to deal with quality of life, okay? So it's part of orthodontic treatment. We have to consider this. So, but what's the goal of the orthodontics, okay? In order to achieve that switch from the disease control to the quality of life, historically, there's quite a change from the goal of orthodontics. In the very beginning, if you look at the late 19th century, it's more focused on dental anatomy, okay? So like defect or type of things, the deformity of the face. So Kinsley was kind of focused on those kind of stuff. And then into the early 20th centuries, Edward Angle started to classify orthodontics to be more focused on occlusion. So it's more function. He's more focused on function to achieve a functional goal. And then later in the mid-20th centuries, that goal has been switched a little bit toward more into the stability of the result. Okay, so the stability of the result is kind of coming from the Edward Angle's orthodontic treatment with occlusion without taking out teeth, and then his student Tweed starting to look into his case and say, hey, maybe we should look at the stability because there's quite a few relapses from those cases. So he proposed this extraction philosophy to make sure it's not too crowded, and when you unweave the crowding, the tissue is still stable and hold the teeth. Okay? But when the evolving into the late 20th centuries, Bill Parker has and his student kind of proposed that facial aesthetics is important. Okay, and the most famous thing he talked about, he said, if you treat a patient and cannot improve their facial aesthetics, then you don't consider that's a successful treatment. So so everything is moving toward that direction right now, even including the appliances. People are looking at the aesthetics appliances, right? For example, you heard about Invisalign. Okay, so those are aesthetic orthodontics. Okay? But all of these need to be in the same bucket. Okay, not because we are talking about aesthetics, so we forget occlusion, or we forget facial anatomy, or we forget other stability issues. No, everything is in the same bucket and going to the treatment goal. It's just which component is getting bigger in that time. Okay, great. So I think right now a lot of attention is in the soft tissue paradigms, which is in that sense. So that's why our patients always, when they finish, always smiling and good, nice facial profiles. And so you can see all those patients that have been treated in that situations. Of course, this not just, some of those are just orthodontic comprehensive treatment. Some of them has gone through the adolescents growth modification to change their facial profile. And some of those pictures here are including orthodontic surgery, using the surgery to improve the aesthetics. So all of those, this is one of the contemporary orthodontics goal is to achieve aesthetics. So how do we go orthodontia transform? Okay, you can if you look at the picture from the left side, we transform the tooth alignment from left side to the right side through the orthodontic treatment, right? So and you can see the cartoon down there. The kids has a kind of funny teeth in there. So and some people say it looks stupid in there, right? Okay. So then you treat them and to move into a more normal face and to get the looks better and to get their self-confidence, everything like that. But there's a black box in here, okay? Orthodontic transfer, okay? What is our prescriptions in orthodontics? In the medicine, you have drug, you have a surgery, you have quite a few things you can use as a prescription, right? In orthodontics, what is our prescriptions, right? So I'll give you a few seconds to think about that question, right? Okay. Okay, so let's take a look. I think input is our force. Okay, if you look at orthodontics, what essentially we do to the patient? Our input is force, right? And our output is tooth movement and facial appearance, right? So those are input and output, okay? The thing is what's connection in between, right? With force input and with the result outcome in there. What's in that black box? It's biology, right? It's biological asset and how the system, our body, detect mechanical stimulations. And then we can do some computational mechanics to understand that. Okay? So if you look at that tooth, that canine, from that position, move to that position, what has been gone through, right? It has to be moved through the tissues. And what tissue is involved on that movement, right? So it's if you look very carefully, you look at the tooth has to be separate in there and has to move inside as a pink gum tissue underneath as bone and PDL. So if you consider this is the particle moving, right? This is moving. It has been moving through those kind of tissue. So and if we take an example in here, what you see here is a baseball, right? A ball, a curved ball. You throw it. And what does ball moving in the nature? They are moving in the air, and they have to separate the air molecule in the front and in order to move ball forward, right? And create some turbulence or mechanics around this ball. And that's how the ball moving. So this is kind of particle moving in the inside the needles. What happened to that tooth when we talk about the canine? Move from the top position and to the normal occlusions. We apply force to that tooth for sure, right? And that tooth will create some type of stress around the PDL periodontal ligaments. For example, you can see this side with the red line is a lot of compression on this side, right? And then have the tension on the other side, right? And then those stress will transfer into the not just PDL, but into the bone and create a stress streamline of the stress. So there's a gradient of the stress inside the bone. And that bone, if you compare with this curved bone has that streamline. You can see those airflow turbulence in there. So this stress is just like our turbulence inside the bone, okay? And those turbulence will trigger the medium to separate so our tooth can move into it, right? But they don't break down the bone. If they break down bone, we're in trouble because then the tooth will fall out. It's become oral surgeons won't take our teeth, right? Okay. So what we do in here is that we put pressure on the teeth and then create pressure in the periodontal ligament, and that stress go into the bone. So what you are seeing here is bone is one of the medium, and that bone has been triggered, and there's structure in this bone, has a harvesting system, has a trabecular bone there, and those bone has a cell inside, right? So whenever fluid mechanics comes into this area, or the bending of the bone, it will create a localized perturbation of the stress, and that stress will sensed by the cell, and the cell is bounding to the matrix, like the extracellular matrix, through the focal adhesion kinase bonding in here. So the stress will alternating those gene expression and then trigger gene expression to trigger the osteoclast formation or osteoblast formation in either way. And when osteoclast formation comes in, then they're starting to break down the bone, just like the curved bone. They separate the air molecule in front of them. So this, if you consider tooth is the curved bone, then that stress creating a degradation of the bone, creating a space, allow tooth to move into space. So this is a part of involvement in the bone. But not just bone, I mentioned earlier, there's periodontal ligament there in between bone and teeth. And this is a matrix in between bone and teeth. This matrix also need to be moved in order to have tooth move, right? So the first hypothesis and the theory which people believe is that when we put a pressure on this teeth, is create a compression on the PDL and decrease the oxygen level, so causing a local hypoxia. Okay, and that local hypoxia will then trigger the inflammation, trigger the inflammatory cytokine expression. And most important one factor which people know is ranitidine. Okay, ranitidine is one where bind to osteoclast and differentiates, causing the osteoclast differentiation and causing the local bone remodeling and bone resorptions. So this is kind of cascade of this, the prescription you put in there as a force, right? And it goes through hypoxia, inflammation, bone remodeling, and then causing the tooth movement. But how about, oftentimes we hear patients say, hey, I feel soreness on my teeth after you put in the braces, after you put in wire, okay? So hypoxia is not the only mechanism. Right now, we have several evidence to show that the receptor, for example, nociceptor sensory nerve also involved in this process, okay? So part of that is when you start putting the pressure into this periodontal ligament, there's a receptor in those AAA1 cells, nerve. They express PSO2 receptor. And PSO2 receptor is a pressure receptor. They can receive a force. And even with a small force, light force, they can receive that. And then they can go around and to create the capsaicin, the pen release the chemofactors and trigger inflammatory cytokine as well, and then trigger the glycan in causing the bone resorptions. So that's kind of another series. So if you look at this, what I just talked about, no pain, no gain. Okay, usually the patient asks them, I tell them about that, right? Okay, and so those are nociceptor we just talked about that mediate the orthodontic tooth movement, and this has been approved in the medical studies. It's occupy about half of tooth movement, okay, in those situations, and those nerves are coming from trigeminal nerve. Okay, so they have innervated into the periodontal ligaments. And so, and what's the pen substance most well known to you? This is kind of receptor, okay? It's called cation channel subfemoral V. It's called triple V1 femoral, which is a receptor in the nociceptor sensory nerve, which receive the pain. But this is chemical receptor. The prescription we described to you a few minutes ago is a forces. That's not chemical, right? So when you are putting your finger on a baby's face, okay, and use very light, right? Use gentle force to push them. They can feel, so they will smile, they laugh, or they cry, right? So those kind of gentle force, okay. On the other side, the right hand side, you see that Oscar 2022, right? Okay, slap on another actor's face. What's that? That's not just feeling. That's not just feeling for smile or things. It's arch, it's pain, right? It's painful. So at the moment that's wrapped into it, the piezo2 receive the pressure, and the piezo2 send the quick signal and have the sensory nerve release ipsissin, okay, and then to release local to feel the pain receptor, okay. So those are the piezo2 information. So to summarize this part of biology, that's why we see that just using the physics as a curveball, right? You put a force on the teeth, and you create the local stress, and then there's two potential pathway goes in there. One is the hypoxia pathway, which is trigger the local inflammatory reactions, and another pathway goes through the piezo2 sensory nerve and produce neurotransmitters and to introduce inflammation, and then trigger the bone remodeling and create degrade bone tissues, and then allow the tooth to move into the space. So this is very fundamental biology of orthodontics. And another thing is that that information, how do we control it, okay? The information needs to be controlled. Otherwise, you can see from here, if information don't get controlled, what happens is keep degrading the tissue, okay? And you're going to lose the teeth, right? So we have to find several ways to control the information. There's a lot of other ways to control. But in this particular situation, we're looking at the autophagy mechanism, which control the information. For example, in this is acid class cell culture, and you can see the green light. Green light is fluorescence, green fluorescence protein, or LC3 reporter, which LC3 is indication autophagy mechanism. Okay, when autophagy happens, they will release LC3. So, which means when we are seeing the cell, like a monocyte starting to merge, become macrophage and merge, like this one, like a bubble, it's become a multinuclear osteoclast, right? So this multinuclear osteoclast formation involves autophagy, okay? So which means autophagy could be a regulatory function in here. And we're looking in the in vivo animal study, we find those autophagy gene and the osteoclast gene marker, they are co-localized, which means they are happening in the same place. So there's a mechanism, autophagy is one of the mechanisms to control the information. If information goes too fast or goes extreme, then autophagy will come to bring them back. And so that's when we do the orthodontic tooth movement, the tooth still in a healthy situation, right? So that's all the biology I want to talk about. Now let's get into some of the mechanics of the orthodontics, okay? In the mechanics, we already talked about force, and force will generate the moment. And then each object which we try to move, like the curved ball or teeth, they all have some mass called central mass, right? And also they, with their different constraint, they have central of resistance and also have a central rotation, which can dictate how the tools will spin, will move in the oral cavities, right? So again, we come back to this little bit diagram in here. Okay, so the force is our perception, and now we understand a little bit of this gray box, how the biology works, right? So then the output is tooth movement, and if you look at this tooth movement in here, we can separate it into 6 degrees of freedoms. Okay, if you look at it in here, okay. Yeah. So what are the 6 degrees of freedom? Each teeth, right? Just like if you do dancing, right, yourself, you can do an forward, backward movement. You can do lateral movement. You can jump up and down, right? And you can bend your body. Same thing for each teeth. We have 6 degrees of freedom, right? So in here, like, you have buccolingual direction, you have medial distal direction, and you have occlusal and gingival directions. And also for each axis, you have a spin, you have a rotation, 6 moment in there. So this, when you apply a force, tooth has those 6 degrees of freedom of movement. Okay? In the face, there's also, if you apply external force, for example, you apply the head gear, okay? And then you can change the face, you can change the growth direction of the face, right? So that will allow you to kind of modify the people's face, adolescents, kids' face, okay, to get aesthetics purpose, okay? So that's all depending how you apply the force. So the force is the important factors, and what's the force? Okay, the force is the key to move the body, right? In the Newton's first law, it says the body changes directions or motions is because of force. So every object, if they move, they need a force, or they need to change that force, external force, right? So how do we do this on the teeth? Okay, on the left-hand side, you see a very traditional, we have done it for more than 100 years, right? Using a braces and using a wire, okay? And then using the braces and wire to apply the force into the teeth. And there's so many modifications in the world, the different type of bracket, different type of wires on that, right? The second system, which is people are talking about, is Invisalign, right? Which is no braces. If you see the left side bottom picture, which is Invisalign, right? So which you don't use the braces, but if you using a tray, plastic tray, to move the tooth, okay? And let's look at how the force happens on the teeth. If you put brackets and wire onto these teeth, and you put pressure on those teeth, right? So what happens? Remember we talked about this pressure when it happens in that area, the red area, right? And the teeth will tip and create enough pressure on the other side in different locations. So those are creating the pressure on the teeth, right? So what's the force? Newton's second law told us F equal to ma is a mass times acceleration. So that's a force. But a force is not a scale or not a single number, right? Okay, you can say 10 newtons force. Sounds like a single number. However, force has several properties. They not just have a magnitude, they have directions. You have to talk about which direction of the force, okay? And you also have to talk about which location the force is acting on, okay? So those are 3 major properties of force: magnitude, directions, and locations. So now it's kind of coming back to the physics you have done in your first year while in your high school, right? Force, when it's applied to this piece of rectangular objective in here, there's a central mass of this object, right? And if you apply force at that center area, So this object will translate, will move parallel, okay, without location and to a distance, right? That's how the Newton's first law, with force, the object will move. But if you put a force in a different location, away from the center of mass, what happens? The object will move the same translation in the same direction. In addition, the object will rotate, right? It's going to rotate because there's a moment in there. Because your force is not in the center of mass, but it's away center of mass. So let's take a picture of the central incisor. If this is one of the central incisors, and you put resistance there, and you apply force, and that's the place you can apply force in the palm, right? Because there's no way you can dig into the root and put a force in there, right? So in this case, you can see the tooth move, right? Tooth move to the directions, but also tooth kick, okay? So the reason we talk about this is because you need to know, is this tipping is the result you want, okay? If it's not the result you want, then you have to control it, right? You have to control your force. Where are you going to put the force? How much force are you going to put in? Do you need another balance moment to do that? Okay, but this has become a moment, right? So moment is created when the force causing a rotation of the body. How do we control those in orthodontics? Okay, there's several tools we use, and I'm just talking about a general rule. Okay, we use arch wire. And there's several different arch wire existing right now. We have a nighttime or shared membrane alloy wire, which is more flexible. And we have a beta titanium, it's so-called a trade name called TMA wire. We also have the stainless steel wire, okay? And also another controller is the brackets. Without bracket, wire cannot do things, right? So wire and bracket has to be worked together. So there's several different type of bracket, like a single wing bracket, twin brackets. There's conventional brackets. You need an O-ring to connect the wire to the brackets. Or you have a self-activation brackets, which using the door on the brackets. You can close the door to housing the wire inside, right? And there's functional appliances, like the removable functional appliances, like the twin block, like the activators. There's a fixed appliances like herbs. Those, for example, this picture showing you here is the herbs, right? So which is kind of pushing the lower tooth forward and bring the upper tooth backward. So this will allow us to do some growth modification of the patients. If the patient has a short mandible or retracted chin, then we can use this type of appliances to modify the growth of the condyles and to allow the mandible to move forward. Another very traditional way is headgear, right? You see the people wear the headgear in the night to restrain their maxillary teeth to allow the mandible to catch up the growth, okay? And also a lot of force we apply, we're using the elastomer, for example, power chains, rubber bands. All those are our tools to use to apply the force. We also can use the coil springs, either push springs or you can be using the metallic ball here for space closure. Okay, and nowadays we have another tool, it's called alignment. Okay, using alignment to combine with some attachments on the tooth, you can using alignment to apply the force on the teeth. So those are all the tools we tend to use right now. And the force is very standard. There's different units people are using. In the United States, they like using Graham. Okay, that's not very, very popular, I think, in Asia or in European. I think Asia and European tend to using the Newtons. Okay, so there's a standard 1 kilogram mass was stored in Paris, right? And that 1 kilogram of mass can be because of gravity. So you times with zero gravity, so you can get the 1 gram. Okay, this is 0.001 kilogram times gravity equal to 1 gram, and then you can calculate this and reverse it. So you can calculate in Asia or in European when you talk about 1 Newton, which is equal about in US we talk about 1.2 gram. Okay, just to run off usual, I just tell students just remember 1 Newton is equal to 100 gram, which is Z. Remember, okay, yeah. But this is where it's coming from, right? So and the equivalent to the gram is centinewton. Okay, Cn. Okay, is a centinewton. Okay. So in the textbook, there's a people gave you some example here to say to tipping a teeth, you need a gram. The force of gram is about 35 to 60 gram, and for body movement without tipping the tooth, which you have to move a lot of tissue in front of the tooth, kind of move into it. So you have to degrade all the material in front of the root surface. So you need more force. You need about 70 to 120 gram for that. And for the root upgrading, it's about 50 to 100 gram. For the location, it's about 35 to 60 gram. Extrusion and intrusion need less force because it's very concentrated. When you extract it, it's on the root tip area or the cervical area. Those tissues need to be liquidated, need to be moved into it. So extrusion is about 35 to 60 gram, and intrusion is about 10 to 20 gram. So this is for single tooth, okay, according to the prof textbook. Those numbers are not all standard because there's some variation on it. Okay? So just a startup, when you start learning orthodontic, it's giving you a foundation to see what's the starting point. So besides force of movement, the most important then is those 3 terms: center of mass, center of resistance, center of rotation, because those were dictating how the tooth is going to move and which direction they're going to be looks like. Center of mass we talked about earlier. If you take a teeth, you extract like all surgeons extract teeth, and you throw into the air, so we can see the pathway of that tooth. That central pathway is the balance point of the free object, and it's the center of mass. Mathematically, you can calculate, okay, a center of mass, okay. And the center of resistance is a deviation from the center of mass, because when your object has other constraint on it, for example, our teeth has a periodontal ligament holding on it inside the bone. So that center of mass is starting to change because of constraints, okay? And those are, when they move, when they are identified, it's called center of resistance. That's the point which resists all the force movement. Okay, so if the tooth is constrained inside the socket with periodontal ligament, then in order to move that tooth translationally, you need to apply the force in the center of resistance. And I want to show you a quick example why they are important to know central mass, central resistance. Okay, so this is one of a case which was treated somewhere else, and so I dig out their previous picture from their previous treatment. So basically, you can see this. This is a self-ligation bracket with a wire they call a super cable, which is very, very flexible. So you can see those wires can flux like this. So huge fluxation. Okay, right? So they say those super cable can move any kind of situation, the tooth malalignment. So very easy to apply to align teeth. Okay, but when patient comes to me, this is how we see. Okay. Did you see the problem here? We see the problem here, right? This round incisor is almost half of root has been exposed because of that force. Okay? So if you look at more carefully how this force was applied to the teeth, right? It's involved the central resistance and rotations. So you can see that this is the force applied to bring this tooth facially to occlusion. However, the neighboring tooth, there's distance. Remember we talked about distance? Okay, there's distance in there. So there's a huge distance in there. And if you look from the side view, okay, so with that force times the distance, you got a moment in there. And also if you look side view on this right hand side, which I connect with the dashed line and draw a loop, right? So you apply the force on that tooth, you apply force in there. So where is central resistance? Central resistance down here, almost maybe 1/3 to the apex, right? So you see, you are not applying the force in that central resistance. It's away from there, so you have this distance d in here, right? And that's create a moment. So that tooth is going to spin in that direction. And that's why you got this result, okay? And this is bad, right? Because potentially the patient can lose that tooth, okay? Can lose the tooth, right? And this happens, the case I saw it at UNC when I was there about almost, I would say 12 years ago. But recently in OSU, one of my residents coming to me is doing case with another faculty, and they have this impacted incisor in there, right? And so they expose this tooth and try to bring into the occlusion. But it's happened again, what you see here, you see this, okay? They try to bring into the occlusion, okay? And then they also expose the root in here. So the principle is always there, right? Okay, force, moment, and where is the center of resistance? So those need to be carefully planned. You don't want to have a situation like this, okay? Because then what you should do as a general dentist, because you haven't decided what you want to do, you are in the D4 right now. So my recommendation is refer to orthodontics at the very beginning. You better not to do those cases. Even with experienced orthodontist can cause a problem like this, okay? So the orthodontic has to control moment, have to control the force to prevent or minimize this thing happens. Okay? So in here, it's just very quick situation to show the simulation. You can see the color change means displacement. Let me see, is this displacement? Okay, yeah, this is displacement. With the red being the high displacement, blue being the low displacement. So you can see the changes of the displacement due to an intrusive band. When I say intrusive band, did you see the Y in here? I have a band coming toward the gingiva of this lateral incisor. Okay, so when we put that band and have a rebound stress, have a rebound, and that's what happens. Okay, and then what you can see is that, let me see if I have enough. Okay, it's easier to see in here. That's what happened. I exaggerate the moment, okay, in this, we call it computational simulation, which is pretty close to the situation you want to simulate. But what I want to show you is that we put an intrusion pen, which try to intrude this tooth into it. You can see this shadow is beginning, and the red is final. The tooth does get intrusion for sure, but the tooth also got a tipping in here, and also got a fretting, okay, which is kind of third order. So you can create a side effect on those teeth as well by putting a single intrusive pen, right? And this is the plot of the same simulation. If you look at the X is the direction of buccolingual, and Y is the direction of intrusion or occlusal gingiva, and Z is mesial distal. So Y is the direction we hope that bend give us a result, right? So basically what you see this arrow, so I have 1, 2, 3, 4, 5, 6 arrows in here. What does that mean of those 6 arrows? If you look at this small corner on the upper right, okay? So the thick arrow which we have is the one is a stainless steel rectangular 16 by 22, okay? And another one TMA, which is beta titanium 16 by 22, okay? And then if you look at another one, the thin one is steel 19 by 25, which is bigger one, right? And another gray and big one is TMA 1925. So which means the bigger wire does give you more intrusion in the Y direction, but they also give you more side effect, like in the Y X direction, which is flaring, and also Z direction, which is tipping. Okay, so both of those give you the direction of side effect. Okay, and then you can also looking at the stress levels in the socket in the PDL level to see where is the stress concentration, because there's different stress components. For example, here you have mesostress. You have compressive stress, which is minimum principal stress. You have tensile stress, which is maximum principal stress. So usually compressed stress will contribute to the acid class differentiation and causing the resorption, and tensile stress will attribute to the bone formation. They stimulate more on acid class reactions. So through the year, there's a lot of modification on the systems and improvement on the systems to allow us to get the finish line quicker and earlier, right? And to get better results. And those are including a lot of techniques like the indirect bonding technique, customized brackets using KCAM design, right? And customized arch wires using the robot bending, okay? And alignment using the computer design displacement, right? So all those can be brought into the area. There's a major contribution is like night high wire type of things. And in the orthodontics biomechanics, we basically divided into 3 stages. The stage 1 is called aligning and leveling, okay? If you look at the picture in here, right upper corner in here, you see the tooth has in-out, major in-out, right? So you need a flexible wire to be able to do that, to have a working range and have a low Young's modulus and can store more energy during a loading state. In the second stage is to either do anterior posterior correction using a rubber band or using the power chain or closing loop to close the space. Then you need a more rich wire. Finally, in the detail stage, you need to be the wire can be bended by your hands and to make stable small changes. So in this this picture, you can see the stress strain curve. You can see strain on the x-axis, stress on the y-axis. So the stress strain curve, you got a linear part in here, and then once it goes to the ear point, the material starts to deform and they don't return. So they are, if you have a strain, you bend the wire that much, it's going to drop all the force in there. It's not going to return, not going to give you return force. So, for example, I draw in here in the dash line is a wire you put in. If you use a rich wire, you move to here, then you are already in the permanent deformation. So you don't get a rebound force, right? So what we do is that in that case, you need some night high wire, which is shape memory wire or classical night high wire, which gives you more deformation, but the material still in the elastic range. They can return to provide that return force. But if you put those steel and TMA like I showed on the left-hand side, it deforms and you lose all the energy in there. You cannot store energy. Okay? So for example, if you have 6% on deformation, you got to have the night high wire. And usually the mild occlusion has a lot of mild alignment, okay, but you need using those flexible byte to do that. So very quickly example, this deep byte case and has a class 2 situation, and we put a nighttime wire in this nighttime wire so you can see you can see the difference. You can see this wire was kind of canine, low canine, and low premolar, huge steps, right? But the material still function is not permanent deform. And into the second stage, then you can correct the AP using rigid wire. Okay. Finally, it's an aligner. It's something coming new, and they try to sell to the general dentist as well, right? So I think you better have a little bit concept on what's the aligner, right? Aligner is using that piece of plastic and design some attachment to let the piece of plastic put pressure on those attachment and removing the tools like this example, the tipping of the crown or tipping of the root, right? And so this is kind of the way they do this is they call it reverse engineering. So you have malalignment in the very beginning, and then they move the tools to the ideal position, and then backward to divide each steps and to provide a series of tray to provide the forces and displacements to move the tools. The effectiveness of the liner is much lower compared to the conventional bracket wire, which on the left-hand side here, this is 3 translational movement. This looking compare the same stage of the movement. You can see the 6 degree of freedom of aligner movement is only half or just 1/3 of that. And same thing for the 3 rotations, tipping, rotation, and torquing. It's only half of that of conventional brackets. So there is differences between the braces and the aligner. Okay, material is different, metal versus plastic. Mechanical is different. Brackets more using the particle movement, the energy conservations. The aligner is creating space using the interpersonal reductions, very similar to the instruction proposed by Tweed, right? And then technology-wise, bracket using very consistent mechanics, and you can using KCAM design as well. But the aligner is using digital design, using some AI algorithm, reverse engineering technologies. And the clinical performance braces has more effectiveness. Aligner, majority of cases we have done is minor case. So now you have 2 options here. Okay, choice. And the future is probably something depending how the development is going to be in the future. Okay, so I think that's end of my talk. Very quick and maybe too dense, but I'm happy to answer any question you have here. Okay, thank you.
Thank you.柯老师，我用中文学生呐，同学，你们这样听得懂基层的技术？我刚才讲那个 mechanic 那个英文这样子听得懂基层的技术？听得懂就好。因为我们现在是希望说，我们将来学生有机会在5年级到姐妹校去然后交流包括日本、韩国、美国等等泰国等等。那到那边当然会有实际的教学啦所以我们今天非常高兴康老师能够在这边跟我们这样做一场的首当其冲的全英文的 lecture。那同学有没有问题？
任何问题？
对，任何问题不一定。
你虽然说很无脑，没关系。
Any question on not only the orthodontist?
Yeah, any question.
有没有要问老师的在俄亥俄州在那边会不会很冷？
现在稍微开始冷，冬天到了，但是还不是很冷。
还不是很冷家燕有没有？
其实我Columbus天气很不错，天气很不错，因为我待过4个地方在美国，一个是 Ann Arbor, Michigan, Ann Arbor， 然后安娜堡比这里冷，安娜堡比这个还北边一点，然后它那边 Michigan 那边的雪也比较多，然后第二个地方去的是Minnesota 是冰天雪地，它有点像黑龙江啊什么大陆的，它那边是很冷，它可以到华氏-50度、-70度可以。然后北卡是我待过最温暖的这几个城市里头，北卡和加州有，比这边稍微温暖的大概5度吧，大概有5度3到5度。那 Columbus 大概是我待过里头算是跟北卡比较接近，就是说没有那么冷的地方。
好，那我们今天非常谢谢那个柯老师就是帮我们，就是等于是 review 了今天跟下礼拜的这个课程。好，那我们会就是希望明年如果有机会的话，也是继续再请老师来帮我们做这个线上课程。好，那最后再请同学以最热烈的掌声，谢谢老师。
然后如果可以的话，因为我不晓得说要放在哪里 ，OK， 所以我是尽量要能够简单，因为我不喜欢讲太深听不懂还好，所以我希望能够得到一些 feedback， 就是跟我说哪边太难，或者哪边可以再 extend。
也祝老师明天是感恩节嘛，还是下个礼拜？
还没下个礼拜。
下个礼拜好，祝您跟你的家人感恩节快乐，然后下个月就圣诞节快乐啊，平安。
好，没错，
谢谢，OK， 拜拜。我们要开始姐妹线交流。